Okay, now it is time to learn how to draw trace portraits when we have repeated eigenvalues. Okay, again here we have two cases. One case is when eigenvalue is positive and the other case is when eigenvalue is negative. Now notice we are only working with 2 by 2 systems. That means we have only a one eigenvalue. So either it's positive, either it's negative, right? Because it's repeated. Okay, so we know always 0, 0 is an equilibrium point. It's the same case in this lesson also because we are dealing with homogeneous systems. So let's take this example and let's say we have the eigenvalue 3 and its eigenvector is 3, negative 1. Now we only consider the natural eigenvector. We do not consider the generalized eigenvector. So one difference we have with the previous section is that really we don't have two eigenvectors. We have a one eigenvalue because it's repeated. So it's one eigenvalue really and a one eigenvector. So here the eigenvalue is positive. Okay, so we know we have e to the 3t part in our solution, right? Eigenvalue is 3. So you have to understand the scenario what happens. So what happens here is when t is small, that means when time is small, e to the 3t is very small, right? So the graph will be like this, e to the t graph. So e to the 3t graph, same shape. So this is t. So when time is small, the e to the 3t is small, but when t goes to infinity, e to the 3t gets extremely large. So keep that in mind. Okay, so what we do is now we draw the xy plane. Okay, and remember what you're going to do next. It's the same steps. Make sure you draw the half line created by the eigenvector. So x is 3, y is negative 1. So x is 3, y is negative 1. So the point is like here. So if you the line, it was a little bit off, it's okay, these are rough sketch. So here we have the half line. Now let's mark the arrows. So we know when t goes to infinity, e to the 3t becomes large. So you start from the origin and your arrows move away, right, when time goes on. So the arrows are moving away. Okay, all right. Now that's done. Now we want to know what happens to the other trajectories. But we know the general scenario what happens. What happens is you start from the origin, right? And then you move away. Okay, so you go parallel to that line, half line from the top. So you move away. Okay, you start from the origin and you move away parallel to this eigenvector. So now from here, the same happens. Now you go downside, okay? Start from the origin and you move away. So this is what happens when the eigenvalue is positive. Now then what can we say about this equilibrium point 0, 0 origin? Is it stable or unstable? It's unstable, right? Because if you have a point right near the original, with time goes on, it shoots away to infinity, right? So this is unstable. So this is an unstable equilibrium point. Now let's look at what happens when the eigenvalues are negative. Okay, so when eigenvalues are negative, so here's an example. Lambda 1 is negative 5, eigenvector is 1, 2. So draw the xy plane, and 1, 2 is like here. So we can draw the half line just like that. It should go through 0, 0. Okay, it's just my bad drawing. Alright, so now we want to know what happens to the arrows. So since the eigenvalue is negative, the arrows are coming towards the origin, right? When t goes to infinity. Why is that? So the e to the negative t graph, as we discussed before, okay, this is e to the negative t or e to the negative 5t. When t is very small, e to the negative 5t is very large. So you are coming away, coming from far away. And when t goes to infinity, when time goes on, you are approaching to 0, right? So your solutions are coming from the infinity. So what happens is, so your solutions are really coming from the infinity and they approach to infinity. 0, right? So solutions are coming from infinity just like this, and they approach to. So from here, from the top side, you are coming from infinity parallel to this line, and from downside you are coming from infinity parallel to this downside line. So this is what we have. So when eigenvalues are negative, of course the equilibrium point is stable, right? Okay, all right then, thank you very much. That's the case.